We're doing it. 3, 2, 1, clap. Ready? 3, 2, 1. All right. Welcome back, everyone. Season 1, Episode 2. Mark your calendars. This is it. We're talking about, I think, FPGAs today. We'll define what that is once I wake up. Yeah. So it's probably good a place to, you start off these things and it's like, I feel, because it's so early for me here, but you got these talk show hosts, like American talk show hosts that start in the morning. They just like are starting with this energy. I don't know how they do it. It's like they got to like fake have energy. And so it's like these talk, they just like are shouting and they do these crazy things. Because when I was in the Navy, I had to drive an hour from where I lived to the Navy base. So I just listened to this. The only way I could stay awake, because I was listening to these like early morning talk show hosts. And they'd all do things like, hey, good morning, Connecticut. I think that's how they woke themselves up. So on that note, let's talk about FPGAs. So Dimitri, who's muted right now in our other thing, so I can't hear him.
I haven't said anything yet. Good morning, everyone.
Okay. All right, so we do, so the premise is we do this class on FPGAs. Dimitri's apparently been doing this for a while. He's got some thoughts on the topic.
For sure, yeah. No, so, it's a topic that always comes up. I mean, people ask us, especially after some of the more basic hardware hacking classes, we always get the question, how or why or when should someone switch over to FPGAs? What's the advantages and stuff like that? And I think if console hacking is a thing, I think it's one of the best examples of whether you're looking at the mod chips that have been kind of effective in the last couple of years against the modern platforms, or whether you're looking at just glitching even smaller devices. You need FPGAs to pull off these sorts of attacks. So, people end up on the FPGA train sooner or later, so to say.
But yeah, so like, one of the, on that note, because I think I had done FPGA stuff in development a while ago, but then I think I just really so I took your class, and then that really was like, oh, wow, this is a little more. I upgraded from the ISE to Vivado, I think at that point. But what's the like advantage there? So because I think that question, speaking of questions that come up a lot, it's like why, and you can do glitching with a microcontroller. So why, like, what's the advantage for people?
I mean, so the biggest, I can just I'll prelude it a little bit with how I got into FPGAs. I mean, when I was doing my PhD just in security and doing stuff with chips and instrumenting stuff in the lab. A lot of times you would need a predictable trigger. You would need to be able to configure it. You would need like something to react in a certain amount of milliseconds, etc. And the only reasonable way to do this was using an FPGA. So, because on an FPGA, you can build a state machine. You can make it predictable in terms of how many clock cycles does it take for something to happen, et cetera, et cetera. So, those kinds of things, you'll even find that on commercial devices that instrument the lab, be it an oscilloscope, some sort of function generator, but also if you're looking at, for example, Risker is a manufacturer that sells kind of, well-engineered in enclosures. They sell essentially glitchers and things like this. And so if you were to open it up, guess what's inside? It's an FPGA. And then on top of it, Josh, I know you and I were talking about, it's kind of wild how much FPGAs are popping up in every sort of device that you see in the data center nowadays. Whether it's on the networking side where almost everything, 125 gigabit is FPGA based, but also just for different types of coprocessors as well.
Yeah, on that note, like Serve the Home is one of the, we're still only sponsored by Josh's Wi-Fi, but Josh's neighbor's Wi-Fi, but Serve the Home, which is a podcast, which is a YouTube channel that both Dimitri and I listen to. I guess there's now the data processing units. They're trying to standardize on the DPU. So this is this concept of basically take like something like a Kintex from Xilinx or something, And then it's basically an embedded system. I mean, that was the thing that kind of blew my mind. It was like an embedded system in the FPGA card, so that it can basically handle all the throughput and everything. Which was, I mean, it's not just on the embedded side. I mean, I feel like there's been a shift. I feel like there's a quote from the Xilinx CEO at one point that they said they're not an FPGA company. They're like a data center. There's some I'm misquoting it, but essentially it was clear that Xilinx was moving into like the data center acceleration market, which is, I think, from their marketing at least, kind of clear. And then their AMD. I mean, we're going to talk about that, like the AMD Xilinx thing. It's even more of a testament to how they're moving into big metal.
Right. I mean, but one would have to, if we're talking about Xilinx getting acquired by AMD, I mean, it all started with Intel getting acquired by, Altera getting acquired by Intel. So now, I mean, True. It's technically an Intel FPGA. So you can see that there's everyone's kind of moving in this direction. But to your point, Josh, about kind of what's happening like on big servers is essentially with these data, with these not yet entirely standardized names for giving you essentially what's happening with these peripherals is you're connecting some PCI Express device that has some form of remote management, and basically it's doing remote PCI Express for you. So it's exposing other PCI Express devices that are being emulated, quote unquote, with all the PCI Express endpoints and whatnot to kind of act like the network card, the GPU and whatnot. And so you can kind of move them into a separate box. So that's obviously an interesting direction. Since we all do security here, I'm very curious how much security has already been thought of in this direction, and how much still needs to happen. How much auditing has happened? Who's going to be the first one that, just like with Thunderbolt, with Lightning and what's the other one? I'm blanking on the name. The other Apple 10 gig port. What's the other one? The USB-C-ish one.
I don't know.
Anyway, you guys will forgive us. There's PCI Express everywhere, so it's a thing. So it turns out once we put everything on PCI Express, you might as well not have any physical devices inside the actual server as well, and you might as well have a separate for you with all your peripherals. Is basically one of the things that you can see happening. So that's kind of, I would say that's the phenomenon that you can see, whether it's with NVIDIA acquiring Mellanox, or with Intel acquiring Altera, or with AMD acquiring Xilinx. This is seemingly the direction that all these guys are moving in.
Yeah, I think we have kicked around the idea of doing some sort of PCIe class, which I think would be pretty epic. But I think we'll have to save that one for our next one, because this one we got ahead of ourselves. And this one was supposed to be the intro, and we got nerd sniped already because we do like talking about these kind of things. But the intro one, right? So this is clearly where things are going. That's why we're interested about kind of this PCIe security topic. But the start for someone who is new to FPGAs, and that's really what the intro class kind of trying to tackles. And so, we go from like zero to it's that joke I think that I've always heard with FPGAs is like, first you blink an LED, then you design a CPU.
That is the classic way that every university teaches these things, I feel. But the irony of it is that kind of the CPU, for all intents and purposes, unless you're going to work at AMD, you might not need the CPU, I would argue. You can do a lot of stuff just with simple state machines, simple man in the middle and stuff like that. So in the class in the intro class that I actually teach, so we did do a previous iteration last year. We actually did it using Lattice, which was nice. The next problem is, like with all hardware classes, is which manufacturer actually has the hardware readily available for you to order. So there was actually, last summer, there was a shortage of Lattice boards, which was kind of annoying for people trying to sign up for the class. I haven't checked if the situation's improved. I mean, the advantage with the open source toolchain is it compiles in seconds. I mean, it's very nice. Unlike it's very, I mean, that's the biggest advantage for me. Like I'll come out and say it, like the fact that you can compile something and run it on the FPGA within seconds, total bonus. But I mean, you're also not getting all the niceties that cause an AMD to buy a Xilinx, which is all the fancy IP that they have integrated on there that you kind of get for free if you live in the Xilinx ecosystem.
Yeah, I mean, I mean, I admit I was skeptical at first. But the kind of compile to the synthesis kind of tool chain to push and then to see the LED blink on a lattice is pretty impressive. But they are different. I mean, like so it's like, the classic Emacs versus VI trolling again, right? So it's like, the thing is that because we use the Digilant boards, and like they have it, like the board is objectively pretty nice. I mean, it has like objectively nice switches, buttons on it. There's just a lot of like the Lattice ones are cheaper for sure. It's also like really bare bones. So it's like
Yes.
if you, yeah.
I mean, that's the issue that we ran into with the class. I mean, you're literally limited to just the LEDs and a single button, if I remember correctly. I mean, it's very bare bones. I mean, whereas the board that we normally use, which is the Digital Arty board, it's actually pretty heavily. I mean, people would say, I'm quoting. I mean, it's hearsay. I'm like labeling it as such. But the thing that you hear from people who work closely with Digilant is that board's heavily subsidized. Is the only reason that it's out there, because if you were to try to make the same board with all those components, you basically would sell it at cost at best. Potentially that doesn't even factor in the manufacturing cost. So it's a big advantage to use the Digilant board instead. But the Digilant board, so on that topic, like for the Digilant board, I mean, what it lets us do is we can actually, so we can blink the LEDs, we can build state machines that react to buttons and stuff like this. And then next time when you're actually glitching something, you're instrumenting something, you're waiting for a line to go high, it's the exact same stuff as pressing a button, flipping a switch. So it's actually super relevant. So the intro class, we take people from never having written Verilog, and we do a bunch of examples. For the most part, we got a lot of positive feedback on that course. Was when we entirely redid it. It's almost entirely essentially like follow me assignments, where we just make the FPGA, the LEDs dance in a particular way, build a state machine, and then we let the students basically have the time to play around with it. And then after, let's say, 30 minutes, we hop back on to show them like, here's one solution, here's one way to do it. And I would say, not everyone necessarily gets every assignment, because sometimes we do various degrees of difficulty. But having said that, it does teach people pretty well on how to write state machines. And so kind of the epic thing with doing this online now is I used to, so primarily going back to when we had actual in-person conferences, I would teach a 4-day FPGA class, and essentially I would do the intro class within just the first day, and which was, in theory, great, right? People couldn't believe it that they would learn FPGAs in one day. But the reality is 2 dedicated days to teaching you Verilog and FPGAs is a little bit nicer. I've seen from the people that have been going through the new iteration of the 4-day class, people have been, I can just see from the feedback that people are much more, let's call it self-sufficient in the best possible way. They don't get stuck as much. So just doing simple state machines, really helps people out in terms of, getting used to writing stuff in Verilog. And state machines, like without alluding too much to the stuff that we go over in our class, basically the easiest thing, whether you're building a CPU or you're building something that controls like a traffic light, what are you building at the end of the day? You're building a state machine. It's always, you're always writing state machines in Verilog. So if you have, the more state machines you have under your belt, the better off you'll be. Yeah.
So then we've got a few FPGA classes up there. So where does this intro one kind of stop to where the next one starts? Like if someone, we kind of get that question a little bit too.
Yeah, for sure. So we also have the intro to hardware class, which we're also going to be talking about on another episode. But the intro to hardware class is kind of going to be the intro to protocols, and like what a 1 and 0 is, and signal levels and stuff like that. The FPGA class kind of assumes that you've seen, data on a wire before with kind of an oscilloscope or a logic analyzer or something like that. And then what we're actually doing is basically the assumption is, you've seen serial data at one point in your life, and now you actually want to interact with it. It's basically where we pick you up. No requirements in terms of, prior knowledge on HDL or anything like that. We actually have, so I would argue, for people who are really well versed in VHDL or Verilog, you probably don't need the intro course as much. Because we do have people, so that we actually get, the funny thing with Verilog and VHDL, they're both popular languages. For whatever reason, VHDL was basically developed in the US for the DoD and only gets used in Europe, and the Verilog's like by a French company and only gets used in the US. I'm hand waving, but you get the idea. So if you know one language, you know the other. So if somebody is doing VHDL on a daily basis, like you're probably fine to take any of our other courses, because we basically do like a 1 hour like breakdown of Verilog versus VHDL, usually to pick those people up. Versus if you've never written code before, Verilog code before, then you probably want to take the intro course. And so, some people though, I know from electrical engineering degrees, I started in electrical engineering undergrad, then I switched to computer engineering. But basically, I remember doing all the logical circuits, doing stuff like counters, almost entirely on building the circuit by hand, right? At least drawing it. I don't think we did as much. I wish we breadboarded more circuits. It would have been more exciting than doing them on paper. Yeah. It's a thing. So if you have that kind of background, you're like completely set. But even for the other people, we go over how does a flip-flop work? How do I build a state machine? So essentially going from combinatorial logic all the way through to sequential logic to flip-flops to registers and all that kind of stuff, and then actually building circuits. And this is the kind of stuff you'd see in control systems, etc. So I do feel that people take it for granted. Kind of think you have to put a x86 on every sensor in a car versus building simple control schemes that either add one or subtract one based on the value that they're reading.
But then how do we get the Pythons on there? We need the Pythons, Dimitri.
That's a separate question. I feel like there is.
Okay.
We might be out of touch with whatever the current language is that people want to put.
This is true.
I think you're trying to say why doesn't the sensor in the car run Node, Josh?
I did just pitch you on incorporating Forth into one of our classes, so I'm going backwards in time as far as languages. All right, so then at the end of the Forth is pretty epic though. I've been fascinating with Forth. I'm going to make the pitch for it right here. If you're doing hardware hacking, and it's not just me. The Hackaday, there's a guy at Hackaday who's also a Forth enthusiast. It's like peek and poke. It's like that Commodore back there. Commodore 64 peek and poke, except it's even nicer. It's like you all this memory protection stuff. You just need dev mem and you're good. This is what you need. The good thing people can see my face, so they can see my facetiousness.
It's called the smug look, smug face.
Yes, the smug look. So, all right. So then at the end of the intro class, what can a student expect to be like? What skills have they? It sounds like they've been able to do state machines in Verilog. They should be comfortable building a bunch of different Verilog circuits, getting these things pushed to an FPGA. Are they at Are they at build a glitcher yet, or is that where does that in the progression of the classes?
Yeah, perfect. So so in the intro class, basically, we do go over how to build like a UART and how to build some simple serial protocols. So usually the end of the intro class, we actually sniff the Lightning protocol that's built into the iPhones, just because it's close enough to UART, where I mean, essentially, like it's not all that different. I mean, if you know UART, you can probably implement the Lightning protocol as well. But on the other side, I mean, so like, nevertheless, I mean, you're kind of missing some of the stuff that you would need. I mean, at the end of the day, if you really want to process data, I mean, like you said, with a Python, I mean, we do write Python scripts in the hardware, in the 4-day hardware hacking and instrumentation class. So the 4-day class, we actually instrument everything using Python. So you kind of have to keep like an eye on where it's reasonable to run stuff on an FPGA and where it's reasonable to run stuff on a PC, in a virtual machine, what have you. So I would argue where FPGAs make the most sense is whenever think of it like you're at the PHY level. I mean, because basically you can output any data of any protocol. You can really easily build kind of an interface to be able to output data, output the ones and zeros, et cetera, et cetera. So yeah, so having said all that, the kind of the example that we do at the end of the intro class is we actually sniff Lightning. So essentially we build a UART and we build a Lightning RX, and then we're able to sniff the signal going over the wire and decode, and essentially you'll see a lot of stuff like the iPhone will say what version of iOS is it running and stuff like that. So that's like part of the protocol. Versus I mean, yeah. So in the 4-day class though, if just for people trying to figure out the difference, in the 4-day class we actually pick up and we kind of target. We have embedded targets. So we have a microcontroller running firmware. And essentially we're hacking it in different ways. So we're connecting to it over the IO. We're using the FPGA and we're doing things that the FPGA is really good at. So for example, side channel analysis is one of them. We do glitching as well on the last day of that class. And the other one that we do is kind of brute forcing. Just that the brute forcing is just a great example of I mean, the crazy thing is the brute forcing I've had, like in terms of hardware pen tests that I've done, I've had it come up more than one time where I was able to brute force a piece of hardware. I mean, where I was able to go through either the password or the pin search space. And a lot of times there, if you're that confident in that the search space is small, all you really need to do is like, I mean, you want to brute force faster. So then you brute force, let's say, 16 times. You connect the embedded device, 16 of them, and brute force on 16 devices because it's some hard-coded password. I mean, all real scenarios that we talk about in the class as well. So having said that, that's where the FPGA kind of holds its own and shines, is where you parallelize something like that. So if you did write a core that is self-sufficient in brute forcing something, well, you can just instantiate it, 16, 50, or however many times. I mean, like the example that we use, we're communicating with another board over UART. So technically you only need 2 pins on the RD. I don't know how many pins you have, but it's probably hundreds of IO that you could use. So you could easily, instantiate 50 instances that would be able to brute force something in parallel if you wanted to. So that's kind of a good example. But so the 4-day class is really about instrumenting and going to the next level and actually using the FPGA for hacking different types of embedded systems and et cetera.
I get lazy and I just instantiate soft core microplaces, and then but yeah, the nice thing about the logic is obviously much more accuracy, but sometimes I get lazy. And then in the Zinc classes, we do a lot of microplay stuff. So
yeah, so you should talk about those as well, because I mean that's like a completely different direction.
Yeah, so so basically if it's what you were saying is that for all the advantages of doing it in Verilog, this is why if you need this kind of fine-grained instrumentation, fine-grained responses, like you're going to have it's clocked at 100 megahertz by default, I think. So you have that level accuracy, which is epic. The problem is that then you just have to do you have to do Verilog, right? So there's not really a problem if you've done Verilog, but then there is some. So the thing is, if you're lazy like I am, what you do is you just instantiate a soft core. So you can in the Xilinx ecosystem, the soft core is a microblaze. It could also easily just be a RISC-V soft core if you really want to be hip. You could easily put that into the FPGA as well, and then you have software control over peripherals. So now it acts more as a microcontroller, but the difference really is that you're building the hardware around the microcontroller. So you add the microcontroller there, you can do C, just like you can. I think that actually the Xilinx SDK is pretty nice for getting like hardware bring up, and then you just add a couple of I want GPIO, I want I2C now. You can just add that around it, and so if you're more comfortable, so it's, I don't know. So sometimes I'm more either just lazy or more comfortable working in like a C environment, and I'm familiar with the microblaze setup. So it's like, I need this to talk to this and hook up a microblaze and then go. And then when it's, but the disadvantage is you have all the disadvantages of having that software. You have to debug, et cetera, et cetera. So there's definitely pros and cons, but it is. I do like the microblaze. I do like me some microblaze.
And then we also have the ultra scale class where I think you went into the deep end of microblazing.
Oh yeah, in the Zinc class. So then the Zinc class I added, I think at least there was one microblaze, and then it was a bunch of crypto accelerators. Then in ultra scale, I was like, well, this thing is so huge. So we did the AVNets. It's hard to find an ultra scale. The Zincs are on the digital boards as well. So I do like those. In fact, I've got one. I always have a Zinc. Always have a Zinc around. So I've got the Zinc. We'll focus. Not focusing, but you always got to have at least one Zinc around. But the ultra scale is like an exponential jump. So it's like in terms of capabilities, size of the FPGA, number of hardcore processors. Because Zinc has 2 arms. The ultra scale can go quad with 2 real-time units. So you just have the amount of hardcore processors jumps up. And there I was like, well, how do I take advantage of this thing? So I did Vivado HLS, which is high-level synthesis, which is, so in the classes that Dimitri does, he does everything pure Verilog. Again, if you're lazy like I am, you'll write it in C and then use the Vivado high-level synthesis tool to convert your C into Verilog. And then it has the most inefficient Verilog, but it works. And then you drop them in. And then what I did is I made a bunch of crypto cores. And I think I had 12 independent crypto cores on the ultra scale, which was pretty, we just added them for the lulz because what else do you do when you have that big of an FPGA?
But so the crazy thing is, right, that, the industry, the rumor, I don't think Xilinx ever confirms this, but half of the IP that Xilinx has in their IP catalog is almost certainly just HLS compiled code.
You could do you have to, it's pretty epic. I would say if you're trying it without, you definitely have to have an understanding of Verilog. I think if you're coming from a pure C background, so I see it on the Xilinx forums all the time. People trying to ask questions about how to obviously make their IP, and they've never done Verilog, so they're asking and it's like the Xilinx forums, the people with the stars next to them are like, guys, you got to learn some digital logic first. So because if you have to write C in a way that you know it's going to synthesize, right? So you can't there's lots of things you can't do. So you definitely, without having any Verilog experience, I think it'd be difficult to do Vivado HLS unless you're writing something really, really simple. But if you've done at least some Verilog, you'll have an appreciation for how synthesis is going to work, and then you'll be impressed with what you can do. I think with HLS. I've actually only done it for crypto acceleration. But you can make, you could also have it. The examples are FIR filters and stuff like this, things that are hard to do in Verilog, where you're just I can make a C function that does this matrix multiplication or something. A Vivado HLS will just eat that stuff up. So yeah, it's pretty cool. And then that's where the benefit is of hooking it to a microblaze, because then you've got these nice 32-bit data width things to connect things. So, but yeah, all that stuff's fun. Okay, so this was largely, intro on the website, it's labeled as Introduction to Field FPGAs, Field Programmable Gate Arrays. And so that's the class we were talking about. The hardware requirements is the Digital RD, yeah?
Yeah.
That's the sole. Yep.
Yeah, so we try to standardize across hardware. So for the FPGA classes, whether it's the intro class, the 4-day class, I would say to a large degree also the applied glitching class, where for the glitchers we rolled our own glitchers. So we built all our own glitchers for all the targets that we did in the applied glitching class. We use the ARTI. Short answer, like we use the ARTI for all those things. So the ARTI's the board, the go-to board for that kind of stuff. For the for the Zinc classes, obviously we're using the Zinc boards, which is also a digital board. It's the ARTI Z7 board that we use there, whereas we use the A7 for kind of the FPGA classes. To your point, one thing that I did want to get off my chest is usually for all the glitchers and whatnot that we write, we'll be under 1% FPGA utilization versus the things that you do with your microblaze.
Yes. You have the, Xilinx will just sell you a bigger FPGA. You got the room. You drop a few microblazes in there. And especially HLS, you'll fill it up pretty quick.
Yeah, for sure. No, but if you're looking at like in the data center, for example, you'll actually see both. So you'll see the Artixes, depending on the use case, but a lot of times you'll actually see the Zincs as well, just because then they can boot an embedded system, and usually, so the I/O might be, usually a typical kind of thing that you would see in modern hardware would be a Zinc to boot, and then a bunch of FPGAs to do the I/O and the PHYs.
And then, and on the embedded side, I think the Lattice has been creeping up more and more as far as just like I/O controllers and stuff.
For sure. Yeah, I know the iPhone has it. For example, the iPhone has a small Lattice. I think it's an ICE 40 of some sort, but I'm pretty sure it's just multiplexing some bus. I'm pretty sure that people didn't use HLS for that one, Josh.
It's so nice. It's so nice. All right. So yeah. So as you can tell, we're FPGA enthusiasts. We've got a lot of classes that deal with either FPGAs or FPGAs SoCs. Check out Advanced Security Training /trainings to see the kind of list of classes. But that hopefully this helps kind of you navigate the website a bit and figure out what classes, and if you're interested in FPGAs, which ones to go. If you're interested in FPGA SoCs, which ones to take there. And so I think this wraps up our.
No, so I was just gonna add. Other industries where they come up. Everything drone related. Self-driving cars. Computer vision is all FPGA based now. Everyone will sell you. There's tons of IP that you can buy. So these things pop up more and more. So even if you're looking at it from a pen tester, understanding what a bitstream is and what kind of memory chip you can pull it out of, because a lot of times these devices are not encrypted. Full disclosure on that one. You would be surprised. I've seen devices that should really be encrypted that aren't encrypted, that have an unencrypted FPGA bitstream, which basically means you can clone it or get keys out of it or whatnot. It can be, it's useful to more areas than Josh and I just get nerd sniped on the data center, and just because the AMD news mostly.
Yeah, well, we a couple things there. One is that Xilinx announced that with Subaru, it's doing the computer vision for Subaru. So there you go. So if you're doing car hacking, the Xilinx Ultrascale actually is the chip that they said they're using in the Subaru car. So there you go, Subaru's for the win. State car of Colorado. And then on the we did that anti-tamper class. That's where we got into a lot of the bitstream protection. So all that stuff you just mentioned in the anti-tamper and puff class, which is we've done a few classes on FPGAs, which is another one where we do. So the second day was all about the physical and clonable functions, and then the first day, we show how to do bitstream encryption, how to do the BBRAM key, all this stuff. So if you're looking to do protection of the bitstream, anti-tamper and puff, we go over a lot of that stuff for the 7 series.
So I think that wraps it up Only other thing I'd add, just for if you're interested in one of the things we want to start doing is whether if you guys want to join Q&A, we're basically gonna have a link. If you guys want, you can sign up, and we'll let you know when we record this, because essentially we're gonna start doing Q&A, take some questions that come in while we record on these kinds of things. So you can sign up and get notified next time we do it live. So yeah, so watch out for that. If you want to be part of this, link's gonna be in the description.
Are we gonna have the live MQTT chat like I had going in the?
I mean, that would be good.
Class. We don't do our chats on the regular chats. You got to use MQTT to chat with us.
I mean, that was very I was impressed. I was impressed, especially when I saw the credit card fly by.
Yes. We'll probably talk about that in a different one. But there's lots of fun to be had. There's lots of lulls to be had on public MQTT servers. So, all right. Okay. So advancedsecurity.training/trainings for the list of trainings. Advancedsecurity.training is the website. And as always, this is brought to you by Josh's Neighbor's Wi-Fi. Why pay for a VPN when you can use Josh's Neighbor Wi-Fi? All right. Signing off.
See ya.